Okay, so we will start. So as we said, we will be doing. Okay, I should just like change this. Also, my background is a bit shivering today, so if I do worse handwriting, just bear with me. So like, yeah. So we'll be starting with projective geometry, obviously. Okay, what does projective actually mean? So like, what do you mean by when you say something is like projective or whatever? So basically, what we mean is, I mean, not really. It's not really the meaning of the word, but the notion usually is like when you're in the Euclidean plane, it's symmetric space. So like the in projective geometry, there is no notion of a distance. So like basically it doesn't exist. So when we are saying like when we are looking at projective statements or working in projective planes and stuff, we don't really see distances. I mean, you can obviously use them by like calculating them from the same definition as the Euclidean geometry, but we won't we won't use it as largely as we did in the Euclidean geometry. Okay, this is just okay, sure. Um, yeah. So now we will be mainly dealing with intersections, cross ratios. Okay, what do you mean by cross ratio? We will get to that in some time. Intersection and cross ratios like project. I don't know how to say that. Project something. Um, yeah. I can just put it to maps or something. Okay. So basically, this is what we will intend to. This is what project geometry. I mean, not really. This is going to cover everything. This is just I don't know. This is how it is different from Euclidean geometry. Okay. So another difference, main difference is we will we'll start with something called like the projective plane. So this is something which is a bit abstract. I mean, it's not abstract. It's very intuitive. If you think projectively, it's abstract. If you think in the Euclidean geometry and stuff. So we will now work in something called the RP square. So Euclidean geometry, like the Euclidean plane that we usually work in, is basically you can say it's an embodiment of R square, right? You can like basically set up a coordinate system and the Euclidean space is just R square. What we mean by RP square is that we just preserve all the things that we have in Euclidean plane, just another we just like add few stuff to it. At the end of every line, like you have this line, let's say, you add a point at infinity. Like basically you have this line which has an infinity on both sides, but there is a point, another point at infinity which you add in the Euclidean, in the projective plane. Sorry, this point will lie. This point is unique to this direction. So basically, any other line you have, this will meet here. Like this point just belongs to everything. So for each direction, you have a unique point. Like b infinity dash, let's say. Like all of these parallel lines just we can say concur at this point at infinity, and there's we add another line which just passes through all this point at infinity. So this is just at infinity. We'll call it the line at infinity. So this is just a set of all points at infinity. Why we are doing this, it might not be intuitive as such. We will just get to that in 1 minute. I'll just speak about this. So while this RP square, so we will get there eventually. Basically, you can replace R by any field here. Like you can get CP square, you can get finite fields. It's fine. But the basically the point is all of these you can represent as a set of, oh, sorry, not a set. Like all the points you can represent as an ordered triple. A is to B is to C, where A, B, C are in real numbers and like not all zero. Like this is not equal to 0, comma 0, comma 0. This is not a very, what do you say? Not a concrete definition as of now. We will get there when we talk about homogeneous coordinates. Maybe not today, but like we'll eventually talk about homogeneous coordinates. So this is where this R comes from. That's why it's RP square. If you change this to like complex numbers, then it will be CP square. Okay, is everyone clear how we define RP square till now? Like the geometric
Yes.
definition, not the algebraic one. Like you can
Yes.
just do this one. Yeah. Okay. If okay, anyone wants me to repeat how you consider points of infinity and a line of infinity.
So when you say that for each direction there is an infinite point,
Hmm.
it's different on both directions, right? For a line, we have two
No. So
directions,
like
right?
no, by direction I just mean this orientation. So this line has only one pointed infinity, which is
Okay,
I
okay.
mean
So even
it's
if you
basically the same
continue to
thing.
the other side, you will still get to
Yeah.
the same point, right?
Yes. So if you just like do this here, like go infinitely over here, the continuity would just go back here.
Okay, okay.
Yeah. Okay. Cool. So now, okay, why? So why did we do this? Like, what was the problem with our normal Euclidean plane and Euclidean plane we were working in? So when we were working in the Euclidean plane, what we had was, so if I give you two lines in general position, they define a unique point. It's true, right? So like I give any like some two lines in general position, they will just give you a point. But when I mean to say that this general position, I mean to say that they are not parallel. So when they are parallel, they do not intersect anywhere in the Euclidean plane. So there is no point which is in common to both of these lines in the Euclidean plane. So we just need to how do you say? Just need to uh, overcome this, overcome this whatever. So basically now when you're working in the projective plane, some interesting properties is that any two lines, like literally any two lines, distinct lines of course, any two lines intersect at a unique point and any 2 points. Okay, when I mean lines here, I also include the line at infinity. And when I say any 2 points here, I also include the points at infinity. So any 2 points determine a unique line. Does this make sense? I will repeat maybe. Okay, let's just like give some examples or something. So basically, let's say if you have this point, let's say point A, and this line L, I'll call this. So this is the point of infinity along L. Can someone try to guess what is the which line is given by line passing through A and the point at infinity?
A line parallel to L at A.
Exactly. So just take this thing, bad drawing, still bad drawing. That's better. So basically, when these are parallel, this point at infinity will also lie on this line. So that's the line we want. Okay, so you have that. Okay, what happens if you take 2 points on the line at infinity? Like you take P infinity and some other point at infinity. Which line is given by these 2 points?
The line of infinity.
Yes, correct. So this is basically gives line at infinity because all the points at infinity lie on the line of infinity. So that's basically line of infinity. Okay, so is this thing like absolutely clear to everyone? Because the stuff we are doing right now is very crucial for understanding things later.
Yes. Yeah.
Yes.
Okay, that's cool. Okay, so now we will do something like, let's say, uh, okay. Now I will introduce some quantity called a cross ratio. We don't know what cross ratio is right now, and like as a matter of fact, for most of the times we really don't care about it. So cross ratio for our scope is defined on three things. One is a pencil of lines. Okay, I forgot to define what a pencil of lines is. I'll say pencil of lines is basically you take a point and all the lines passing through the point form pencil. So if you think these are all the set of concurrent lines. Similarly, this is a pencil of line and a line at infinity because all of these concur on this point of this direction infinity. Is it uh, okay? Does anyone miss
Yes.
for both of them? It's either clear or do you want me to repeat? Are we doing recap of the previous class? Not exactly. We are that like I'll be repeating some part of it, but eventually nicer stuff. Okay. I'll ask again. Is like does anyone want me to repeat what a pencil of line means? Like you can't stay silent for both of them.
I think it's fine. But it's just fine.
Yes. Yes. Okay. So avoid annotating, guys. What is this? Okay. So we have this. I mean, is it avoid annotating? Yeah. Um. So we'll define cost on a pencil of lines. Then we will define it on a line, like just a points on line, basically. Points on a line. Basically, if you have a line, just like set up the points on the line. Nothing deep about it. And a point at infinity, of course. Third thing we'll define it as is it's on a conic. Okay, you don't need to like know what a conic literally means because we will probably be defining conic this way in this class. So we defined on cluster on conics. So basically points on conics. So what is a cross ratio? It's basically a function which takes in 4 points. Let's say A, B, C, D, or 4 points or 4 lines by the thing lines in a pencil. Like I can just say L1, L2, L3, L4, and it gives you a real number. Yeah. So for now, we do not know what a cross ratio means. Like we won't really care about it in most of the times, like except when it's -1. But like I'll just keep it a black box for now. So basically, we have a cross ratio, some function. We will see why this is like good. So it just takes in 4 elements, like in order, of course, and gives you a real number output. Yeah. So this is what we mean by a cross ratio. Now, a cross ratio on a pencil. So when you have cross ratio on a pencil, what you do is, let's say you have like line L1, L2. 3. Okay, for just for saying it now, in this thing when we define points and infinite line and infinity, I just want you to be very clear that like after this point, points and infinite lines and infinity are nothing special. Like P infinity, L infinity, these are not special. Like by special I mean by special I mean special. Like these are not special. Like L infinity is as general as you can as any other line in projective plane. Does everyone understand what I mean?
Yes. Yeah.
Okay, that's cool. At any point, if any of you just like feel that no, like I want you to repeat anything, just like either send me a DM in chat or like I prefer if you speak it out. If not, send me a DM in chat. It's fine. So if you have let's say 4 lines, L1, L2, L3, L4, what we do is we compute. Okay, we have to use angles, guys. Sorry, very sorry. So like it's basically a sine of. By this I mean a directed angle. Like it's essential to take directed angles L2, L1. I mean, it's like L1, L2. Like basically you take this angle in this direction. How do you write that? I think it should be L1, L2, right? Yeah. Upon sine of angle, it is L3, L3, L2 into sine of angle L4, L2 upon sine of angle L1, L4. So this is the um like cross ratio of L1, L2, L3, L4. We define it to be this way. Let me just L1, L3, L3, L2, and upon L1, L4, L4, L2. Yeah, good. So this will be defined this way. Also, for the most of the time of this class, I mean, I think almost all the time of this class, in whether it be points or lines, we will be just assuming that they are different. Okay, sorry. So we'll be assuming that these are distinct. Like the cases when they are same is like really not interesting at all. It's just like you get one or sometimes you get one, sometimes it's not different and stuff. So like they are really bad. So when I say that we are using the cost ratio, I'll just say that they're distinct. So yeah, this okay. This doesn't really matter in any way. Like this just this is just how you get a real number out of it. Um, we will use this at some points in time, mostly not today, but like it's good to remember. Okay, after this, what we do is on a line, right? We will define what a like on a line or on a conic, we will define what is meant by perspectivity. And like when are you allowed to take perspectivity and stuff. So if you have a line and a point not on the line, this is like really important. So P does not belong to L. Can you see that every point on L corresponds to a unique point, unique line through the pencil of P?
Yes.
Yes.
So, like we can say that there is a bijection between every point on L and lines in pencil of P, like pencil through P or whatever. So basically, if you get one point here, you can just like take the bijection, like take this line defined by that stuff, and you will get every line. Uh, Similarly, if you have the pencil, you can just project onto the line on the point that it intersects L with. obviously. Okay. Note that P does not belong into L is like a really important condition here. So when we say by taking perspectivity on a line through a point, we have line L and any point P. You basically uh, like we will have some points under consideration. You basically now view these as a pencil of lines through P. You are allowed to do this as long as P does not belong into L. And for the other way around, like let's say some lines are under consideration and you take any transversal, you can now shift your focus to these points only when L does not pass through P. Like when it passes through P, it's like I mean you're not allowed to do that, but if you just see why you're not allowed to do that, it's you have a like it's just not a bijection anymore. When P belongs to L, all these lines like all these lines will just correspond to L, so it's not a bijection anymore. So L does not pass through P. Is that clear?
Yes. Yeah.
Okay. For the second thing, conics. Okay, should I define it? Okay, yeah. So, okay, for now, we will define conics in a certain manner. So, like, this is an equivalent definition of conics. So, let's say you are given 4 points A, B, C, D in the plane. Yeah, 4 points in the plane. General position, no, what do you call? No, no.
What do
No
I
three
say?
collinear. Sorry?
No, nothing.
Yeah, so no three collinear. Yeah. What we define a conic to be. Okay, how many people already know what is a conic? Like they have a general idea about what a conic is or what a conic means. Okay, so okay, sure. That's a good number. So what we'll say now is a, and we are given a certain real number k belonging to reals, like any real number k. So k belongs to so P is the set of all points in the I'll say projective space now. So P is like RP square such that PA, PB, PC, PD is equal to K. This like conic is a set of points P such that this holds. Is it clear how we are defining the conic to be?
Yep. Yeah.
Yes, cool. So we have this. Okay, so now can you think of when you're allowed to? Okay. So you are given 4 points in like 4 points in a plane. If I ask you what is the cross ratio of this, you can't really answer that, right? It just depends on what conic you are looking at.
Yes. Yeah.
So, like it's just different for different conics. Like if I take a ellipse to this stuff, it will be a different thing. If I take a, I don't know. Okay, you get the point. Hyperbola or something. It will be a different cross ratio. So now can you think that okay so let's say we have a gamma which is a conic.
It just confirming again.
Yeah.
K is a constant. It's fixed, right?
Yes. K is constant fixed. So as like for fixed ABCD, as you vary K, it will give you the family of conics which pass through A, B, C, and D. If that makes sense.
Yeah.
Yeah. So now you have gamma conic. Um, let's say so you have some A, B, C, D belonging to gamma. So can you think that now for what condition on P can we take a perspectivity such that the cross ratio is preserved?
P is on the conic. P is on gamma.
Exactly. So P should lie on the gamma. P should lie on gamma. P belongs to gamma is the condition when you can do that. Similarly, when can you project it onto a conic? Like if you have a pencil of lines, when can you project this on some conic such that the cross ratio is preserved?
When sim again when P is on the conic.
Yes, precisely. So you need some conic passing through this, and then you can just take this stuff. Okay, an interesting thing that you might have noticed is that when you are taking perspectivity, or when we are taking these maps, by maps I mean like A, B, C, D, you are like on a line through a line or on a thing, you are taking this to be PA, PB, PC, PD. These are all strictly bijections. I mean, they are bijections. Bijections are strict. So these are like bijections always. So another thing you can see why we cannot like project onto a conic which doesn't pass through P is that you will have double intersections. Like this line, will you project it here or will you project it here? Do you get what I'm trying to say? Or should
Yeah.
I
Yeah.
rephrase?
Yeah.
Yeah. So this is the case. Okay, one more thing in which is special for conics or like whatever. So if you have a conic and point P on this, obviously all the points A belonging to gamma, when you take perspective to P, it will get mapped to PA. What do you think point P will get mapped?
Point at infinity. Some
Um, we
point.
are we are mapping to a pencil. We are not mapping to a line.
Itself.
Sorry?
Itself or like okay we're to a line. Okay, so the tangent line to the conic.
Exactly. Precisely. So you can see that as we like, let's say this is some point R. So you have to take this line and like move this close to P. This will tend to the tangent. So the line PP would mean the tangent to the conic. Same thing while projecting back. If you have a tangent to a conic and you're projecting it onto the conic through some point P, it just gets mapped to point P. And that's why it's a bijection, right? Because like otherwise the tangent won't get mapped to anything and
This is sort of an equivalence between points and lines. So we can treat them indifferently. Right?
okay, sorry, can you repeat? I just
We
lost
can
you.
treat points and lines indifferently in the sense we can go back for
Exactly,
the whole
exactly. So
material.
we can like project to like take if you have a points on the conic, you can project through a point on the conic, and now the statements, whatever you are saying about those, gets transformed to a to a pencil of lines. Precisely. So you have this. So this is like important thing to know that PP gets snapped to the tangent of tangent to the conic. Okay, let's see what else. Another thing to note is these are, I mean, these are you probably know it by now, but whatever these mappings we are doing, these are bijections associated that, but they are also continuous. Like continuous, I mean, if you tend a point to some point here, then its image will also tend to the image here. Okay, I think I should do one thing before this. That
How
if
do
you
we
are,
know that?
sorry,
I was just wondering, how do we know they are continuous though?
okay, yes, will get to that. I think I should have shared this later. We will get there. So basically, another thing that I want to note is that so if you have a pencil of lines, P, like A, B, C, D, let's say, or whatever. So if you are given PA, PB, PC, and like you want to fill this is equal to some real number K, these things get fixed. Can you see that?
Yes. Yeah.
So as you vary this line, K just varies over real. So this is what you call a injective function or something. Yeah, injective function. Like if you,
Yes. Okay. So it should be continuous. Yeah.
wait, I think, yeah, so, okay, sure. You can probably see that directly because I said the perspective is of cost ratio, but yeah, okay, sure. We will get there. Shall
Yeah. Because of
So,
that.
yeah, exactly. So you note that fixing cross ratio at 3 points also fixes the fourth point. This is like very important to note. Okay, so now we will get to that how do you have cross ratios on a line? So if you have a line and 4 points, how do you go about defining the cross ratio A, B, C, D? Any ideas? Okay, we probably know from the first class that this is basically AC upon CB into what is it? Well, basically divided by AD upon DD. But like just forget that you know it for now. How would you from what we did till now, how would you go about trying to define
You
this
take
thing?
any point outside the line, draw draw a pencil in lines, and then take its cross section.
Yes, precisely. So that is actually a non-trivial statement to say because when you're saying that you are defining it this way and then we're
It
taking a
should be
random point.
constant, right? Yeah. So
Yeah, exactly. So it should be constant for any point P. That is like a wonderful statement. That no matter where you take this point P, like anywhere except on this line, maybe you can take this side anywhere. This cross ratio of the pencils is just preserved. To prove this, to see this, I think the sign rule would be the best thing to do. Like whatever the sign stuff we had, you can show that that is indeed equal to AC upon CB whole divided by area upon DB. Note that as we are using directed angles there. Okay, I should have asked you then. Are people comfortable with directed angles? Well, something in the chat.
Yes. But like, okay, sometimes it may be. But yes. Yeah.
Yeah. Okay. So by directed angles, what we need right now basically is just that anti-clockwise is. I mean, one direction is positive, other direction is negative. That's all we need for now. So basically, angle L1 comma L2 is negative of angle L2 comma L1. So when you are saying that take this angle and take this angle, these are just negative. Should I repeat this? I think I should repeat this. Just like,
we are taking the angles mod 180 degrees side.
am I taking those? I think so. I think so. Yes, sure. You can wait. Can you say give me a minute? Okay, you can say that. But the thing is, that I'm not talking about this angle. So when you talk about this angle, it's basically this angle. And when you take this angle mod 180, you get this angle.
Yeah.
If you get what I mean.
Yeah.
Is it fine?
Yeah.
By the way, are there any buffer problems? I don't want to disturb, but
Okay, yes, sure. Okay, I don't have anything picked out. I can just like give. Okay, give me a minute. I'll just like I'll just search for one thing.
sure, sure.
Okay, do you know what pole polar is?
Should I answer?
Yeah,
Yeah, I do know what that.
So have you done this? Like if you have a circle, like and a point here, like P and Q are each other's polar, then circle with diameter PQ is orthogonal to.
Yes, yes, I've done it.
Okay, sure. Then I should do for another problem. Interesting. Oh, what can you see on the screen?
Your thing, but like there's some black thing for a minute. So.
Okay, okay, sure. That's cool. Okay, I had not paid this problem before, so I just giving you a random problem I solved. I don't know what the problem is. Is that fine? Oh no, I think this one is good. Have you done shortlist 2005 G6?
Yeah, that's a known-ish one.
Oh my God, you have done everything.
I think Ivan has a cross ratio handout, so maybe that will have some problems if you haven't done it.
I'm finding from there.
Oh, okay.
Uh, okay, this is probably I think this is quite trivial if I remember correctly, but maybe you can do it. Like if you do it, just give another one. I should have done this earlier. Okay, I just posted to okay, just post on Zoom if anyone wants to try. This is the buffer problem. Yeah. Okay. So anyway, it's a good time to take a break. Is any what everything we covered till now? Does anyone have any questions? Like, just feel free to ask if you want me to repeat anything or you didn't understand something.
No, it's all clear.
Okay, that's cool. So we'll continue. So
Yeah.
we know that we get directed angles here, and that is why you can also get negative reals because like obviously sign of negative numbers is like negative. So when you do the same thing here, this you need to take it as directed lens. Lens, yeah. Basically, when you take something to be what is it? Yes, so basically you just assign a direction randomly. So now AC upon CB is negative because AC vector like AC is a different direction, CB is a different direction, and AD upon DB is also negative. Like, in this case, it's negative, but in the other case, it might just depend on how you place those points. So it's very crucial that you take directed lens. Otherwise, obviously, you will only get restricted to positive reals and you won't get to negative reals. Okay. So this is how you do it. How you define a cross section on a line. Important thing to note is that this thing is not the definition. It's a consequence of the perspectivity. So it's like a consequence of how you define it. So surprisingly, it's okay. Chat. Oh, okay. Sure. I'm sorry. I didn't have any profile problems. Very sorry. So yeah. So important thing to note was that this is just independent of this point, which is like really cool because it's very surprising. Yeah, so that's how you define it on the line. On a conic, you don't have a good definition. Like I don't know of a good definition to do it. Like the length thing and stuff. You just like take a point and project. The good thing happens when the conic is a circle. Yeah. So basically, the point was that if you have a if you so yeah. So in if you're thinking projectively, so you don't have a notion of distance. Sorry. Yeah. So distance like doesn't exist. How would you differentiate between a circle and something like ellipse or a hyperbola, like circle and any other conic? Like we just like circles because it's just too good. But if you're working here, there is no way you can define a circle or identify a circle with more precise or differentiate a circle from any a general conic. I mean, you can just try if you want. So like basically, how would you define a circle in general? It's just this is equal to radius, but you can't do
Can you
distances.
say it through angles? Like,
Sorry.
can you say it through angles? Circle is a curve. But if you take any 2 points
Mm,
and you take any third point on the curve itself, the angle is the same.
I mean, sure, but like if you see, we don't really know what an angle is. The what we have here, where did I go? Like the sine thingy was just like a way to quantify stuff. And the interesting stuff is it doesn't depend on the angles. Like, okay, that would be a bit confusing now. What I mean is it just depends on the cross ratio of those angles. Like this what we have here is just preserved irrespective of no, not irrespective of what angle do you have, but like, irrespective of
So you're not defining the cross ratio through angles. You're defining a cross ratio through some kind of, it's a function that remains invariant.
yeah, it's like sort of like you have. I mean, we have to use some notion of angles somewhere, but basically, like when you take a projective map, like okay, I'll get to this. I'll just speak about it for something. So what I mean is when you take a projective map, by this I mean like perspective or homography or whatever. What the things that are preserved is cross ratios. Cross ratios are preserved, lines are preserved, and incidences are preserved. Incidence by I mean like a point lies on a line that this image will lie on the image of the line. So when you take a projective map, these things are preserved. Angles are not preserved. So like angles are not preserved. What else is not preserved? Like distances are not preserved. I mean, distance is not preserved. You can just see it directly, right? Like, if I have something like this thing, surely this is not equal to this, like clearly. Similarly, ratios in general are not preserved. Like let's say, like for example, you have something like let's say you have two parallel lines and you have 3 points. You have these concur. Like then you know that these ratios are preserved. But now since like we can take any two general lines, obviously these ratios are not the equal, right? Like you can just check that out. It's fine. So yeah, so when the thing is actually a circle, we can now quantify the crosses on a circle as you can quantify the crosses on a circle as basically like basically the same way you determine like so AB CD would be AC upon CB into what? What is this? AC upon CB into where do I get confused? DB upon AD. Note that I mean in circle you can define directive distances as like this stuff and this stuff sort of stuff. I mean not really maybe I'm not sure. But the general way to assign sign to this is basically that if A, B, C, D, this is positive if and only if, oh, this is negative. Okay, give me a minute, I'm confused.
So here AC is the length of the chord AC, right?
Yeah, these are lengths.
Yes.
These
Okay.
are lengths. This holds like only for a circle. Like this
Why
is a
is
circle,
this, by
it's
the way?
not a circle.
Is this
Sorry?
just a consequence of the same angles?
Yeah, I mean, you can derive that if you want. I'm not really interested in doing that. So, like, if you have something like this stuff, you can have this point P here and like project this stuff. Since it's a circle, you will get some relations and just like direct stuff.
Okay.
Circle is just nice because
Okay.
I mean, if you want, we can do it later, but that's not really the fun part because we won't use it anywhere after that. Yeah, so this thing is negative only when wait, I'm really confused. I forgot. I think it's A, B, and C, D intersect inside the circle, like the chords A, B, and AC. Okay, we can just check this out. So for a
I think more if the arcs overlap completely or something like that.
sorry.
More like if the arcs overlap. If like CD is inside arc AB, then it's positive. If
That's
CD and AB are completely disjoint, I think it's that.
that's
Oh,
equivalent to
is it?
saying the intersections inside the circle.
Oh yeah, it's the same thing because like at that point they will intersect outside. Even if they're here, they will intersect outside, right?
Yeah.
Yeah, so that's how you assign the sign to this. But basically, again, this is just a quantification that's not how you define a cross section on a circle. The definition is just you take a point P, you project, and you take perspectivity. Yeah, okay, so I think like we should talk about this earlier, but we can just talk about signs on lines. So again, lines also. Like if you have stuff like A, B, C, D on a line, it's again the same thing. If C and D both lie outside, then it's positive. If exactly one of them lies inside, then it's negative. Both of them lie inside, it's positive. So like both inside or outside is positive. Exactly one inside is negative. Does that make sense?
Yeah.
Okay. Anyone has any questions till now? Like
So
literally any question.
for a
Sorry?
circle, when you are given just 4 points, and you say like the formal definition is just to take a
Yeah.
circle, take a point P on the circle, and then project the 4 points of the circle on a line, and then take its cross ratio.
Okay, you can say that, but if you remember, I started with crosses on the pencil. So
Okay, so okay, you take it as a pencil of lines. That's
yeah.
also fine. But uh, yeah, okay, no, sorry, I got it. I was doing something else.
Okay. Sure. So basically you have this. Okay. Also another thing to importantly note is that let's say if you have some conic. Okay. Now I'll just stop saying conic because we will really never use conics. Like we will use them in some points of time, but not really right now. So if you have this point P, you can basically project this line onto this circle and vice versa. But the like just to think have a back of your head is you are not really going from a line to conic directly. You are really going from line to pencil to conic. Like you can just like do this stuff and like you will have some tangent line. Sorry. You will have some tangent line. You will have this parallel line for infinity, which will intersect the circle somewhere else and stuff. Like there is this intermediate step. I mean, we will usually like skip it most of the times, but you just need to be careful that is this intermediate step of taking a pencil. So basically, it's line to a pencil and like then to a cone. Similarly, when you are projecting from a line to a line, so basically, if you have these two lines and you are like projecting from some random point P, then like you have these 4 points. Wait, which is the point? So this point, and projecting them onto these points. You are basically taking this line to this pencil and then projecting onto the other line, if that makes sense. Is it okay?
Yes.
Like we will skip it most of the times, but it's just good to know and like have it on the back of your head. Yeah. So okay, so we are done with this stuff. We are done with this. What next? Yes, so now we will get to the interesting part, which is really harmonics. Like, why did we do all of this? What's the relevance of this? Like, harmonics is just a special. There are ways in which you can use general cross-ratio chases, but like, so just to give an example, it's basically if you get some, you can A B C D1 is equal to A B C D2 on same locus, like some line or something. Then you can conclude that D1 equal to 2, right? Because we showed that it's injective. Does it make sense?
Yeah, yeah, that was
Yeah.
from before. Yeah.
So, I mean, at this point, we don't care about what the value of the cross ratio is. Like, we really don't. I mean, we usually never care what the value of cross ratio is. Okay, it's too long to write, whatever. So, like, that's why I said that we can just treat it as a black box. Just note that crosses are preserved under projective maps. So that when you take perspectivity, project, and stuff, we will get like there are more projective maps, of course. We will get to them. Should I do it right now? Should I do it later? Um, um, okay. Let's just let's just do it right now. I think let's just do some projective maps first. Yeah. So projective maps. These can be between like lines, conics, pencils. These are maps of. I mean, just as the word suggests. The projective. I mean, they are bijective. They preserve cross ratios. Yeah, I think that's it. Like some of these we don't I think required. Like if you said, I'm not really sure about this, but if I remember correctly, you can just drop some conditions because you can derive them from other stuff. But it's budgeted, preserve cross ratios. Yeah, the continuous thing now we will like I just write it as just properties. It's not really like conditions because you can derive some of them from others. Basically, continuous how you can derive them is let's say you're projecting from a line to a conic. Oh, sorry, line to a pencil. So what we have here is that uh, um yeah. So if you tend this point like this is like A B C D. If you tend this point D to this point, then the cross ratio will basically tend to A B C D. When you take perspectivity, it will the cross ratio will tend to P A P B P C P D, and hence the like this line will just tend to this line. Okay, does it? I don't think it made a lot of sense. Did it make sense?
Intuitively, it is very clear to why it is continuous, but I mean, it's not a proof.
Okay, yeah, I'll try to like formalize it. So, okay, we'll just okay. What we will do is assume that yeah, assume these two that it is by I don't really it just preserve cost ratio. So f is some map from okay. There's some special letter for this, but I forgot what it is. Um, I'll say an object one to object two. By object, I mean this stuff, lines, conics, or pencils. So if they are like A, comma B, comma C, comma D belonging to O1, you want to show that f is continuous, right? So um, if you take f of A, f of B, f of C, f of D, so take a point E which tends to D. So now you have that. Uh, what do you have? Okay. Um, A, B, C, E. I mean, cross ratio. I'll start with f of a, f of b, f of c, f of e.
What was E again?
E is the point which we are tending to D to show that it's continuous.
Okay, fine.
Yeah, so E is equal to A, B, C, E. Now, since we are tending it to E by the cross-ratio thing, you can see that this is equal to, I mean, I should probably say tends to or something. Like whatever, you get the point. A, B, C, D. But this is again equal to f of A, f of B, f of C, f of D. And so you get this stuff like f of B, f of C, f of as E tends to D, this thing tends to this thing. So f of E tends to f of D. Does it make sense?
Yeah.
Okay. Does it make sense to everyone?
That makes sense.
Yeah, okay. Okay, wait. There's something in chat. What is it? Okay, never mind. Yeah, so you get there continuous and things. Yeah, what else? Okay, so we were discussing projective maps. I'll just get out of it because for some reason. Yeah, so okay, can you think of some example of projective maps? First is like perspectivity. It just covers all the things that we did before this. Do you know or can think of any other maps that might be projective? Or like just guess randomly, it's fine.
Inversion?
Yeah, inversion is projective. Important thing to note in inversion is that inversion on a plane is not projective. Like if you see inversion as one of like a function from plane union pointed infinity to, to the same thing, this is not. I mean, like inversion in general on a plane is not projective. This is because it's not really bijective. Like if you invert about say point A, it goes to some point at infinity, right? You don't know which point at infinity.
Okay, yeah. Other than that one case, fine. Or
Yeah, I mean, so we will see. So inversion, swapping two things like inversion from one of these objects, like if in O1 to O2, this is definitely projective. Like let's say if you have a point passing through this thing, and now you invert this circle about this point with some radius, and this goes to this line. This is definitely projective because now you know that this point basically goes through points right along this line
yeah, okay.
because we are considering this line.
Yes, yes.
Similarly, if you have like a line passing through it and you invert, okay, it's basically the same line, so it's fine. Yeah, and if you have like a different circle, then it maps another circle, so it's still fine. Does anyone get inversion? So swapping two objects is projective.
But it's not trivial to say that inversion preserves cross ratios, right?
No, it's not trivial to say that.
Okay.
Yeah, I mean, I think I'll just say trust me on this.
But it is true, right? It is true.
It's true. You can somehow prove that it shouldn't be like too hard. Oh wait. I think is it trivial? Uh, it's probably trivial, right? Because like these lines are just preserved.
Yeah. Uh, tangent pointed. Yes, okay, that also.
I mean, doesn't it matter? Tangent will intersect somewhere else, like somewhere
Okay.
here, and the line at
Yeah,
infinity will like go here.
yeah,
Yeah,
makes sense. Okay.
Okay, so it's okay. So it's probably
yeah,
trivial. So yeah, that's what I need to like clarify once again that infinity is not a special point. So like tangents not don't always go to infinity. I mean, in fact, they will like rarely go to infinity. They'll just intersect the line at some other point. So infinity is nothing special. It's just this random point you have here. It's just like parallel stuff, but it's not really special if you think about it.
okay.
Similarly, tangent is nothing special. It's just like the point coincides, so it's fine. Yeah, so inversion is projective. That's true. Okay, we will mostly be using these two, just I mentioned some other stuff. Isogonal conjugation is projective. In case, okay, I don't know if everyone knows. I don't think I don't know this, but if you have a triangle and if you have a triangle and some random conic passing through, like if you said a random conic passing through it, okay, does anyone have heard about what is isogonal conjugates?
I think like it's something to do with equal angles that it makes with the vertex or something.
Yeah, okay, so I'll just say that. So basically, what an orthogonal conjugate is, you have this thing, you reflect all of these about the angle bisector, respect to angle bisectors. So basically, this angle equal to this angle, this angle equal to this angle, this angle equal to this angle. Then all of these concur another point. It's not non-trivial to show that, but just like trust me on this right now. I mean, it's not very hard, but you can do it. So these two are said to be orthogonal conjugates of each other with respect to this triangle. You can extend this definition to points at infinity as well, like this the same stuff you do, like just take the perspectivity through A, like take perspective through A, reflected about the angle bisector and stuff. So that's orthogonal conjugation. It's not. I mean, okay, I'm just saying this for the sake of saying it. It's fine if you don't really understand it
Where
also.
did the conic come from then?
Yeah, I'm saying. So if you have this, then it's a fact that if you have a circumconic of a triangle, by it I mean it passes through all the three vertices, and you take like the isogonal conjugates of all these points, they will lie on some line. Like under some conjugation, it goes to some line, not passing through any of the vertices. Again, it's not able to show that, but you can like do some stuff and show it. Like okay, when all the things I'm saying that you can show it, but I won't show it right now. You can just talk to me later if you want to know about it. It's fine. I'm just saying it because that's not really quite interesting. So the interesting thing is that under isogonal conjugation, circumconics swap with lines. So trust me on this right now. But the other interesting to say is that this preserves cross ratios. Cross ratios are preserved. So basically, if you have 4 points here and take all of the isogonal conjugation down this line, they will still share the same cross ratio. Is it fine?
It's a map is to take the conic to the line, right?
Yes.
Okay, yeah.
Yeah. Another thing like I was saying to say is that if you have, let's say, 4 points fixed, and like this is a point and a random line, and like you are defining a map from this line L to the line L itself, where you map every point E to point E dash, which is the second intersection of all like 5 points determine a unique conic. So there will be some conic passing through all of these, and since like it's degree 2, it will intersect L at a second point. So you map E to E dash. Uh, Again, this is projective. This map is projective. Proof of this is actually like quite easy, but for that you require another theorem. So we will do that. We will do it after we do that theorem.
Can you repeat the thing again?
Yeah. So if you have a point E, you consider the conic passing through A, B, C, D, and E. Note that it's a unique conic because 5 points determine a unique conic. That conic will intersect L at a second point E dash. Second point E dash might coincide with E if it's like the tangent to the conic, but you get the point. Like if for example this conic is something like this thing which is tangent to E, then E dash will basically coincide with E. So this E maps to E dash. This is a isogonal conjugation. This is a projective map. It's like not uh, trivial to see it, but again, we will do this later. Why this is a projective map?
So this is a projected map where you're sort of
Sorry?
This is a projective map when you take in consideration 4 points and a line, right? And a line passing. So,
Yes.
yeah, meaning, okay, phrase it.
Yeah. Yes, better.
Wait, actually, I had one doubt about the previous one. I couldn't resolve it by myself.
Yeah.
So, if we take the point to approach one of the three points A, B, and C, where does the isochronal
Okay.
conjugate?
These are under bijection except points A, B, and C. I should have
Yes,
mentioned. So like this
but
is
then,
not an A, B, C. Yeah.
but then, what are the three arcs of the circumconic go to?
Sorry, I didn't get your question.
What are the three arcs of the circumconic go to then? Are there three different segments which
Okay,
happen
that is
when
very
it is cut by
very
the
interesting.
three lines of the triangle?
Okay, that is really interesting. I've not thought about it. We should see that because um okay, if you see a circle go maps to the like circumcircle of ABC. So if you have a circumcircle of ABC, what am I drawing? Yeah, this maps to the line identity. So if you have points on this stuff, oh, wait. Okay, I'm not really sure about this. It's just my guess that it will be these like we will just exclude these 3 points from the final thing. I that is just my guess. I think
Okay.
so because because the point is if you take this point, oh no, it's actually consequence. It's also always still exists. Oh
That would
yeah,
split it
yeah.
up into 4 segments. So
Sorry.
that, yeah, that
No,
would that
it's not only 4 segments because the pointed infinity is like the same thing.
okay.
Yeah. So like because if you take this point, it's like my bad. I forgot to mention this. Okay, it's a very good thing that you reminded me. This isogonal conjugation works for except the lines. Like this thing is except line. Like I should say here. Okay,
Okay, thank
thanks a
you.
lot for pointing this out. Yeah, like it's interesting. Like the isogonal conjugation works on planes except for lines AB, BC, and CA. Yeah, because the points on these don't really have isogonal conjugates as such. So when you consider these lines, you just basically exclude those 3 points. And when you take a circumconic, you just basically exclude ABC when mapping. Okay, thanks a lot for asking that because that's really good. It's a very crucial detail. I should have not forgotten that. Okay, does anyone want me to repeat what happened right now about the isogonal conjugation or in general about this thing also and anything?
And so you just said the isogonal conjugate thing because you cannot define the isogonal conjugates for points lying on the lines ABBCC.
So basically, you just exclude these 3 lines while defining orthogonal conjugates and taking orthogonal conjugation. So for this line, you will exclude these 3 points, and for that, we will exclude ABC. Okay. Nice. I think this is clear as well. If you have any questions, this is the time to ask. I should try the chat. Anything in the chat. Conic also. Okay. That's I think. Yeah. Okay. So this was about projective maps and stuff. So basically these are the maps that preserve cross ratio and we will like use them a lot of times later. Okay, I think we are a bit low on time still. So now for the first time we will actually care about what quantity the cross ratio is. So what we now care about is harmonics. So what are harmonics? Harmonics is basically when the four things, by this I mean conic, line, pencil, whatever, is -1. Like -1 is very specific. Okay, why -1 is specific? If you observe, if you take k equal to like this, let's say if you for k equal to 1, I said you get the cases like c equal to d or something like that, because you get that ac upon cb is equal to ad upon db. So like, there is a unique point which divides segment AB in a fixed ratio, so you'll get C equal to D. It's not really interesting at all. And the so K equal to -1. Also, when like the by the formula we know that A B C D is basically 1 upon A B D C, right? By the formula we know it, because AC upon CB upon AD upon DB, you just swap those.
Yeah.
Someone was asking something.
Oh no, I was just saying yes.
Okay. Yeah, cool. So you know this. So when the ratio is -1 specifically, the interesting thing is that a what is this? What am I saying? Okay. Yeah, A B C D is actually equal to A B D C is equal to -1. Does that make sense? Because like the inverse of -1 is just -1.
Yes.
So now this is a so now this I don't okay. So this is the thing. How does this help us? How does this help anyone? Is if you have a line, if you have a line A, B, like I'll draw C and D, this one, because now we know it's negative. This is a harmonic bundle. By this we call this a harmonic bundle. So we call this is a harmonic bundle if AC upon CB is equal to negative of AD upon DB. Negative is only because of the sign. So if you just like look at the ratios in the absolute sense, you get that mod of AC upon CB is equal to mod of AD upon DB. Basically, every point here is uniquely mapped to some other point there, such that the ratio in which this divides internally is the same ratio in which this divides externally. Does that make sense?
Yeah.
Yeah. Okay. Okay. Just two quick thing we have. Okay. If you say this is also a projective map, by the way, that like map every point to its harmonic conjugate. So that's a projective map. So like you take any point C, you map it to its harmonic conjugate. That is a projective map. I don't think it's very trivial to see why projective map, or maybe it is, I don't know, but it is just this. So we will maybe add it here. So let it go. There is a really bad notes that take harmonic conjugate. Oh wait, I forgot to say one projective map. Okay, so I say it now. Okay, let's complete this first and then I'll say it. It's more, yeah. Let's complete this first. So yeah, this divides internally and this divides externally. Okay, no, I think it's the right time to say it. So there's another projective map that we have, which is like very interesting. Like it's like really interesting. So if you have a conic and a point, okay, I'll just draw a circle because it's just better. And a point not lying on a circle, maybe inside, maybe outside. Quick question. Can we take perspectivity through this?
Can you
Okay,
repeat what you said? Can you repeat?
yeah, so if you have a point P not lying outside the circle, can you say this? Can you say this thing?
Yeah,
Can
I would.
you?
P should be on the conic. Yeah.
Precisely, P should be on the conic. So this is not equal to this because P is not lying on the circle right now. Okay, for this is a circle, like I mean for sure on the circle. So P is not lying on the circle. So you cannot say this that P is PA, PV, PC, PD. But a very interesting thing is that if you take like the lines through this, like any line through P which intersects the circle will intersect the circle a second time, right?
Yeah.
So okay, I should adjust this one. I'm thinking. Yeah, you have these things. And then you have, oh my God, what is this? Oh my God. Oh my God. Yeah. You have this thing. And you have, let's say, two tangents. I am really sorry with the handwriting and diagrams, but I can't help it. It's fine. So
You,
if
you
you,
can try shift, maybe that will make a straight line.
oh, does it? Oh my God. Where were you all this time? Yeah. So you have this stuff. If you map A, so what we consider a map in this case is you map A to second intersection of PA cap circle, second intersection. Like second intersection in general, if it's a tangent, it's basically the same thing because they are coincident points. So this map is projective. So let's say if you have points like A, B, C, D, then their images are A dash, B dash,
So we have the same
C,
cross ratio. Any 4 points, which
yeah, C dash, D dash. So you have that A, B, C, D. This is not equal to PA, PB, PC, PD. Note that. But it is equal to A dash, B dash, C dash, D dash. Yes. This is what we have. Cool. Is this clear to everyone? This projective map. This is very useful. We will use this a lot of times.
Yeah. Okay.
Okay. So we have that. Now we will get to harmonic quadrilaterals. Okay, harmonic points on conics, they are interesting, but let's not go there right now. We will just, oh, okay. I mean, okay, circle is just a conic. We'll
by
do
the way,
conic.
just to go back to the earlier thing,
Yeah. Which one?
uh, the circle. Yeah, this one only. So
Hmm?
here A prime, B prime are interchangeable, right? I mean,
Yes.
okay.
Wait, what do you mean by interchangeable exactly?
Meaning the cross ratio would still be same if I replace A by A prime.
Uh, you need to replace all of them. You need to replace A by A prime, B by B prime, C by C prime, D by D prime.
No, but
Because it's not the same as the line PA. That's like important because this is not equal to line. This map is from a circle, like circle, conic, to the same conic. Also, it's important that it's the same conic. By the way, it should be the same conic. You can't do this for any other conic. So this map is from conic to the same conic. You don't have an intermediate pencil step here because it's just not allowed to do that. Why you can think about it that way is if you take a pencil, then the map is no longer bijective because these two will map to the same line. So basically conic to the same conic. You have this thing, and if you have point somewhere here, oh my God, I can't draw anything. Yeah. So basically this point maps here. So if this is A, this is F of A. If this is B, this is F of B.
so what I'm saying is when you're taking the cross ratio ABCD,
Yeah.
and that should be equal to the cross ratio FA, FB, FBS, FP.
Yes.
Yeah. Here, even if is here, the cross ratio of FA, BCD and A, FA, FC, FCD would
Oh,
still
yeah,
be
yeah.
equal,
You
right?
mean to say we can
Yeah,
do this?
exactly.
Yeah, yes, yes, we can do that.
Okay.
That is because this is an involution. By
Okay.
involution, I mean,
Okay, if you apply it 2 times, it will still give the same thing.
yes, precisely. So basically, like, just remember this term involution because eventually this is like a projective term. We will eventually classify involutions in this manner. So you have this thing. Yeah, okay. I hope this is clear to everyone. Okay, we are almost out of time. We'll do harmonic things on a conic and then maybe stop. So harmonic points on conic. So okay, so I think both the last stuff we'll get with the next class. But if you have harmonic points on a conic, I'll just draw a circle because it's easier to draw a circle, but it can literally be any conic no one cares. Okay, I think some of you would already know that. Okay, anyone wants to say how to classify harmonic quadrilateral?
When the cross ratio is harmonic.
I mean geometrically. Okay, that's cool. No one knows, so this would be interesting. Is harmonic quadrilateral like if ABCD is -1? Yeah. Oh, sorry, ACBD is -1
Yeah.
because like AC are opposite points, so that would make it -1.
I think I said that.
Yeah, yeah, no, I mean this is like the definition. This is what I say when it's a harmonic quadrilateral. But
Yeah.
do you know when this holds? Like
That's-
when does this happen?
No. No.
Okay, that's good. Now we will try to derive it. Derive it in the sense like we'll just try to do it. So yeah, we have this. I'll call this circle or conic omega. So like these are all on omega. Okay, what is the only thing that we know about harmonic stuff
Oh
that
wait, I
doesn't
got
hold
it.
for a sorry?
AC is the AC median of BAD. Yeah.
Yeah, I mean, sure that you get that, but it's like a consequence of what we will be doing.
Wait, no, I think this was in EGMO, right? Chapter 4, it's there.
No, that is true. That is true. What you said is true. That like if you have a triangle and like you have a circle, a circumcircle, and you take the median, then this quadrilateral is harmonic. What we're saying is absolutely true. Uh,
Right.
yeah. What I'm saying is, okay, for this I should probably say that this is like on a cyclic coordinate. Okay, I should
Yeah.
probably disallow this from this section because like this holds when omega is a circle, and that is the thing what you are saying that. Oh, what is this? Omega is a, sorry, yeah.
BD, AC cap BD and the tangent from A intersect BD will be harmonic, right?
Yeah.
AC cap BD and tangent from A to mid BD is harmonic. Yes,
Yes.
precisely. So this is what we know. Like this you get by projection, right? So basically you have that AC BD is equal to -1. You use the projective map where you're taking pencil from A. Like for now, I will write it or pencil will like just uh, stop writing it later. AC, AB, AD is same as -1. So here this is equal. AA is the tangent. Is AC is just AC and this is just. So you have these points are harmonic, P and Q. So you have that Q, P, B, D is -1, right?
Yeah.
Okay, now can we take the perspective from C? Let's see what happens when we take perspective from C. You get CQ, CP, CV, CD is equal to -1. Now project it onto the conic back. Okay, you will get CQ. I will just leave this for now because we don't know what CQ will map to.
But then the tangents from C and D intersect on BD.
Exactly, exactly. We are trying to prove that or derive that. So we'll just leave this blank for now because we don't know what it maps to. This is A, this is B, this is D is equal to -1. But since it is -1, we know that we could swap these two, right?
Yeah.
So from this, we know that this is also equal to CABD.
So your mystery thing is C.
Yes, so CQ is actually CQ actually maps to C, which means CQ is tangent to the conic.
Yes.
Does it make sense?
Yeah. Yeah.
Yeah. So what we actually have here is that this is the same tangent and same for B, D, and D. So B and D, okay, it's a really bad diagram. B and
Yeah. So
D,
this also gives median. This also gives.
yeah, exactly. That's why you have that in triangle. If you just take tangents at B and C and join A, that's the symedian.
Yeah.
Okay, did you have a conflict class here? I don't think so, right? Or did you?
Not sure, but I know a bit.
Yes, so like it's fine. Like this everything relates to conflicts perfectly. So basically this AC and tangents to BD intersect on line AC. So that's what we have when 4 points on a conic are harmonic, harmonic but on a conic. For circle, this gets better because now we know like good ways to qualify things on a circle. Like tangent is perpendicular to line joining center. It's like angles are very nice and stuff. So we get that in a circle. Okay, we are like a bit over time, so I would not start with polar stuff now. I intended to cover, okay, it's fine. We covered a lot of stuff. So I think you will have another projective class. So we're probably looking at like polar, Broca, Pascal, I mean Brancon, obviously. So these are some stuff that are very useful in problems. We will cover this probably in the next class. Okay, in case those who are interested, Pascal's theorem, you can just look it up online or something. I don't know. Or you can ask me, I can tell you if you want after the class. So in case you look up Pascal's, the thing I said here that where is this?
That thing you can show easily one of the transformations.
Yeah, this thing is like basically a two-liner proof from Pascal.
It's saying that the conic maps to the conic, right? That one, right? No, okay,
Yeah,
no, no,
like
no.
this
Okay,
point
yeah,
maps to this point.
yeah.
That is a projective map. You can show it by proof from Pascal. Just like okay, quick note to add, we saw many projective maps here. Composition of projective maps is projective. That's like it's like really easy to observe that. I just want to write it down. The composition of projective maps is projective. This is like a very trivial thing to observe, but really powerful. Do people know what composition means? Like it basically
Yeah.
means yeah.
Yes.
So if you like take two projective maps one after the other, then the eventual map that you get is projective. So you can prove this using Pascal's. It's basically a two-line proof.
If I remember, it's just saying that they are concurrent. That's all.
No, Pascal's is okay. Okay, I'll talk about this. So basically, the class is right now over. So if you want to
Oh,
leave for
right.
dinner stuff, you can go. I'll stay here. I'll just talk about it for some time if people are interested. Let me stop the recording.
Yeah.
How to stop the recording? Yeah, stop recording. What is happening? Oh my God, I can't stop it. What? Yes, finally.